Hello friends, welcome you all in third part of description, that is the UV visible spectroscopy part 3. Then content of presentation we have covered in the part 1, introduction to UV visible spectroscopy, principle and instrumentation. In part 2 we have covered Lambert's law, types of transition in organic molecule and application. In last time, part 2, we was unable to cover too much about the effect of conjugation, effect of solvent and application in detail. So hence in part 3 we are going to see all these things in detail. So what is the effect of conjugation in the UV visible spectroscopy? So if any molecule is very conjugated, so that type of absorption is happening at the longer wavelength in the UV. If any molecule is non-conjugated, so it shows the absorbance or lambda max towards the shorter wavelength in the UV. Hence the conjugation of double bond require lower energy for the transition. Molecule having conjugated double bond exhibit absorption band within the ordinary range. Example, butadiene in an hexane. It shows absorption at 217 nanometer. As number of double bond in conjugation increases, absorption occurs towards the longer wavelength. If enough number of double bond present in molecule, then absorption maxima shift towards the visible region. Means if number of double bond is more or increasing, so absorption automatically we are getting towards the visible region, and that solvent or compound is showing color. For example, 1357 octatriene in hexane. It shows absorption at 296 nanometer. Beta carotene, it has 11 double bond and naturally occurring yellow color compound or pigment. It is a very conjugated type of compound, hence it is showing absorption length or absorption at 451 nanometer. Means absorption maxima happening at 451 nanometer in the visible region. If ethylene type of compound, only single double bond is there, then compound show absorption at 170 nanometer and butadiene at 217 nanometer. So from all this we are seeing that as number of double bond increases, absorption maxima is shifting towards the longer wavelength. So this is the effect of conjugation in the UV. Then next is the solvent effect. Solvent effect means if paracetamol is a compound and if we are dissolving in different four types of solvents. Suppose paracetamol is dissolved in the water, paracetamol is dissolved in the HCl, paracetamol is dissolved in the NaOH dilute solution, or paracetamol is dissolved in the water which contain the little bit amount of HCl. So what happened? This type, what changes we are observing, we can see. So if paracetamol is having the more solubility in NaOH, so it is showing absorption at 257 nanometer. But when paracetamol is not fully dissolved in the water, it is not showing that much proper absorption, and it shows its lambda max at another wavelength. And in HCl, it is also not very stable, so it is showing lambda max at another wavelength, as well as absorption maxima is also shifting, and the amount of absorption is also shifting due to the solvent effect. So first is the red shift. It is also called as orthochromic shift. This shift is happening towards the longer wavelength. So if any compound which is when dissolved in the particular sample or solvent, then absorption is happening towards the longer wavelength, then this is called as red shift. When peak is shifting towards the shorter wavelength, then it is called as blue shift. Then what is hyperchromic shift? If due to any effect, if absorption increases, then it is called as hyperchromic shift. If due to any effect, if absorption decreases, then it is called as hypochromic shift. Then next is the very important term chromophore. What is chromophore? Chromophore is originally the term chromophore was applied to the system responsible for imparting color to the compound. Means earlier it was defined as any compound which is giving color is a chromophore, but nowadays the definition is modified. Now chromophore is defined as any isolated covalently bonded group that shows a characteristic absorption in the UV region or visible region is called as chromophore. What is oxochrome? Oxochrome is not a chromophore, but an oxochrome is responsible for shifting of wavelength towards the longer region. So an oxochrome can be defined as any group which does not itself act as a chromophore, but whose presence brings about a shift of absorption band towards the red end of the spectrum. Oxochrome group do not show characteristics absorption above 200 nanometer. Some common oxochromic groups are OH, OR, NH2, NHR, NHR2, SH, etc. So all these are the oxochromes. Next we are going to see in detail about the applications of UV visible spectroscopy. So first is the detection of functional group. Not exactly as like IR we can define the functional groups by UV, but this technique is helpful for detection of particular chromophore, or we can guess the presence of that type of functional group uh, according to the wavelength of absorption of the compound. If any molecule is showing absorption in UV, then we can say that that compound is having chromophore. If it is not showing any absorption, so we can say that it does not have chromophore or it does not have unsaturation. That compound can be saturated. Next is extent of conjugation. So addition in unsaturation with increase in number of double bond shift the absorption towards the longer wavelength. If the absorption occur in the visible region, that is at about 420 nanometer, then that type of compound is the Pauling type of compound, and hence the absorption as number of double bond increases, the extent of conjugation also increases, and the absorption is shifting towards the longer wavelength, that is the redshift. Next is distinguish in conjugated and non-conjugated compound. By UV, we can distinguish the conjugated as well as non-conjugated compound. In the slide we are seeing that first compound and second compound both are the isomers, but one is the first is the conjugated compound and second is the non-conjugated compound. Hence the conjugated compound is showing absorption towards the longer wavelength than the unsaturated compound. So by this if we are having the isomers, so we can distinguish conjugation and non-conjugation by their appearance at particular wavelength. So always conjugated compound shows absorption at longer wavelength than the non-conjugated compound, and we can distinguish the type of compound like this by this. Then identification of unknown compounds. Unknown compound can also be identified if we are having the known spectrum of compounds or we are having the library of known compounds, then we can identify the unknown compound by UV. Then examination of polynuclear compound. Benzene or polynuclear hydrocarbon have characteristic spectrum in the UV region. Thus, identification of polynuclear hydrocarbon can be made by comparison with the spectra of known polynuclear compounds. The presence of substituents on the ring generally shifts the absorption maxima towards the longer wavelength. Then elucidation of structure of vitamin A and K. So this UV visible spectroscopy is very helpful for elucidation of structure of vitamin K. Here we can distinguish the vitamin K1 and K2 and also A1 and A2 by UV. Then identification of compound in different solvent. So as we are changing the solvent, absorption changes. For example, chloral hydrate. Chloral hydrate shows absorption maxima at 290 in the solvent hexane, while if we are dissolving in any aqueous solution, then disappearance of absorption happens and we are not getting any absorption. So hence as we are changing the solvent, we are getting the different absorption maxima. Then we can distinguish cis and trans type of compound. Means determination of configuration of geometrical isomer is also possible by UV. Example is cis-stilbene and trans-stilbene. Cis-stilbene shows absorption at 283 nanometer, while trans-stilbene show absorbance at 295 nanometer. Means trans type of compound shows absorption towards the longer wavelength as compared to cis type of compound. Then we can distinguish axial and equatorial position by UV. Substituent at axial position shift the wavelength towards the longer position. Then detection of impurities. UV visible spectroscopy is one of the best methods for determination of impurities in organic molecules. Additional peaks can be observed due to impurities in the sample and can be detected compared with the standard raw material. By also measuring the absorbance at specific wavelength, the impurities can be detected. In the structure, we are seeing that in the standard PCM, that is paracetamol sample, we are getting the spectra. But if paracetamol is having the impurity, we are getting the extra peaks. So extra peaks indicate impurities in the sample. So by this way we can identify impurities in the sample by using UV visible spectroscopy. Then qualitative analysis. It is also applicable for little bit for the qualitative analysis, as UV visible spectroscopy can characterize those types of compound which absorbs UV radiation. Identification is done by comparing the absorption spectrum with the spectra of known compounds. Next application or last application is quantitative analysis. So by using the Beers-Lambert's law, we can easily quantitate any type of compound or any analyte by using UV. So UV absorption spectroscopy can be used for quantitative determination of compounds that absorb UV radiation. This determination is based on Beers' law, which is follows as A equal to ABC, where capital A is the absorbance of sample, small a is the extension of coefficient, B is the path length, and C is the concentration. So by using this formula, we can identify the concentration, as well as by getting the line equation also we can quantitate any type of analyte by using UV. So this is the major application of quantitative analysis. This is the major application of UV. Thank you. Here we have completed the UV chapter. Thank you so much.